The Venusian surface exists as an inferno, a landscape of immense pressure and scorching heat, where lead melts and the atmosphere itself is a corrosive furnace. Human engineering currently offers no viable method for permanent surface habitation, presenting an ultimate environmental challenge. This renders conventional colonization impossible, demanding an entirely novel approach to sustain a human presence. Yet, approximately 50 kilometers above this hostile surface, a remarkable zone exists. At this altitude, atmospheric pressure approaches Earth-like levels, and temperatures hover around a temperate 30 degrees Celsius. Within this ethereal band, a unique opportunity for atmospheric colonization emerges, defying the planet's otherwise lethal embrace. The foundational principle for a Venusian cloud city relies on atmospheric buoyancy. A habitat filled with a breathable nitrogen-oxygen mixture possesses a density lower than the surrounding Venusian atmosphere, which is predominantly carbon dioxide. This density differential generates lift, allowing the structure to float as an aerostat within the benign atmospheric layer. Construction demands materials of extraordinary resilience. Lightweight, high-strength composites are essential, offering resistance against sulfuric acid present in the upper atmosphere. Advanced polymers, carbon fiber laminates, and ceramic matrix deposits form the primary structural components, engineered for long-term integrity within a corrosive environment. The structural design of these aerostat habitats will likely favor spherical or toroidal geometries. These shapes distribute internal pressure uniformly, minimizing stress points and maximizing volumetric efficiency. Modular segments, capable of independent deployment and assembly, will facilitate expansion and maintenance in orbit before final atmospheric insertion. Life support systems form the critical core of Venusian habitation. Closed-loop ecological systems will be paramount, meticulously recycling water, oxygen, and carbon dioxide. Atmospheric processors will constantly monitor and regulate internal gas compositions, removing trace contaminants while maintaining optimal breathable conditions for the inhabitants. Power generation primarily relies on photovoltaic arrays positioned strategically above the densest cloud layers. These arrays capture the intense solar radiation available, converting it into electrical energy. Advanced battery storage systems are necessary to ensure continuous power during Venus's prolonged rotational periods, safeguarding critical systems. The external environment, rich in sulfuric acid, necessitates advanced atmospheric processing and shielding. Specialized filtration systems will continuously scrub ambient air for particulate matter and corrosive aerosols, protecting the habitat's exterior and internal systems. Regular maintenance cycles will involve robotic inspection and repair of the outer hull, ensuring structural integrity against the elements. Climate control within the cloud cities will maintain a constant, comfortable internal temperature and humidity. Excess heat generated by inhabitants and systems must be efficiently radiated away, while internal atmospheric pressure remains stable against the external differential. Advanced thermal management fluids and radiative panels facilitate this crucial environmental regulation. For sustained operations, a robust system for resource acquisition is vital. Water, a precious commodity, can be harvested from the Venusian atmosphere itself, where trace amounts of water vapor are present. Condensation and purification systems will extract this moisture, supplementing closed-loop recycling and reducing reliance on external resupply. Unlike terrestrial cities anchored to solid ground, Venusian cloud cities require dynamic station keeping. Thruster systems utilizing stored propellants or atmospheric mass drivers will counteract minor drifts caused by atmospheric currents. This active stabilization ensures the habitat remains within its optimal altitude band, avoiding descent into hostile layers. Communication with Earth and other orbital assets demands resilient relay networks. High-gain antennae, protected from the corrosive environment, will transmit data through Venus's dense atmosphere. Orbital satellites, strategically positioned, will provide continuous links, enabling scientific data transmission and mission coordination across interplanetary distances. The sheer scale of a Venusian cloud city dramatically contrasts with conventional orbital stations. Where orbital habitats maintain vacuum pressure differentials, a cloud city manages substantial internal and external atmospheric pressures. This requires a fundamentally different engineering approach, balancing buoyancy with structural robustness rather than simply sealing against a vacuum. Unlike the Moon or Mars, where gravity is significantly reduced, Venus possesses gravity comparable to Earth's. This eliminates the need for artificial gravity systems benefiting human physiology. However, the environmental threats are far more immediate and pervasive, shifting the engineering focus from microgravity mitigation to atmospheric survival and material resilience. Terrestrial habitats are protected by a thick atmosphere and a magnetosphere from solar and cosmic radiation. Venusian cloud cities, suspended above the thickest protective layers, will require robust radiation shielding. Layers of water or specific composite materials integrated into the hull design will mitigate these energetic particle fluxes, safeguarding inhabitants. Internal logistics within the cloud city will rely on efficient, modular transport systems. Automated shuttles and pneumatic tubes will move personnel and resources between habitat segments. Maintaining internal atmospheric integrity across interconnected modules demands sophisticated airlocks and pressure regulation, ensuring compartmentalization against potential breaches. Food production within a Venusian cloud city necessitates advanced hydroponic or aeroponic farms. These controlled environments optimize nutrient delivery and light spectrums for maximum yield within confined spaces. Recycled water and synthetic fertilizers, derived from atmospheric elements or imported, sustain these closed agricultural ecosystems. Waste management protocols must achieve near total recycling efficiency. Organic waste will be processed through biodigesters, generating methane for energy or nutrients for agriculture. Non-organic waste will be compacted, stored, and potentially recycled through on-site material printers or ejected towards the lower atmosphere for incineration. Despite the relatively benign upper atmosphere, Venus's weather systems are immense. Powerful atmospheric currents and electrical storms could subject cloud cities to significant mechanical stress and electromagnetic interference. Advanced meteorological forecasting and active thruster systems are critical for navigating or avoiding these vast dynamic weather phenomena. Over extended operational periods, even the most resilient materials will experience degradation from the trace sulfuric acid and constant radiation. Regular structural inspections, robotic repair units, and a comprehensive material replacement schedule are essential. Failure to mitigate material fatigue could compromise the habitat's structural integrity, leading to catastrophic failure. System failures represent a constant threat. Malfunctions in life support, power generation, or station-keeping thrusters could render a habitat uninhabitable. Redundant systems, fail-safe protocols, and rapid response repair crews are non-negotiable requirements, ensuring that no single point of failure can jeopardize the entire city's operation. A gradual loss of buoyancy could result from gas leakage or an increase in the habitat's mass. This would initiate a slow, irreversible descent into the hotter, denser, and more corrosive lower atmosphere. Continuous monitoring of lift-to-weight ratios and the ability to inject additional buoyant gas are vital to maintain the optimal altitude. The ultimate catastrophic failure would manifest as a breach in the pressure hull. A sudden rupture, whether from external impact or internal overpressure, would expose the interior to the extreme Venusian atmosphere. The ensuing rapid depressurization and environmental ingress would render survival nearly impossible for any exposed inhabitants. The psychological toll of living in a perpetually isolated, artificial environment presents a unique challenge. Extended periods without natural light cycles, terrestrial landscapes, or direct exposure to an open sky can induce severe psychological distress. Designing habitats that mitigate these effects through simulated environments and robust social structures becomes paramount for long-term crew well-being. External impacts, though less frequent than in orbital space, remain a threat. Micrometeoroids or atmospheric debris could compromise hull integrity. While the dense atmosphere offers some protection, high-velocity impacts could still cause localized damage, necessitating rapid detection, isolation, and repair protocols to prevent widespread decompression or environmental contamination. Economic sustainability for such an endeavor is precarious. The immense initial investment and ongoing operational costs require substantial and continuous Earth-based support. Developing self-sustaining industries within the cloud city, perhaps utilizing Venusian atmospheric resources, is essential to reduce dependency and ensure the project's long-term viability beyond initial scientific objectives. The construction of a cloud city on Venus transcends mere engineering. It represents a profound statement of human persistence against an indifferent cosmos. Suspended in a temperate band above a hellish surface, it would be a testament to the capacity for adaptation, a vibrant island of life in an otherwise barren sea of planetary extremes. Such a city would function as a perpetual laboratory, its existence a constant experiment in environmental resilience and resource optimization. Every breath, every watt of power, and every moment of human occupation would signify a victory over the crushing pressures and corrosive elements that define Venus's natural state, pushing the boundaries of survival. The light reflecting from the metallic hulls, a beacon in Venus's upper atmosphere, would symbolize humanity's evolving relationship with its solar neighborhood. It would mark a new chapter where worlds previously deemed uninhabitable become canvases for our ingenuity, where the very act of existing redefines what is possible beyond Earth's confines. The cloud cities would offer an unparalleled vantage point for atmospheric and planetary science, unraveling Venus's geological and meteorological mysteries. They would serve as launch pads for deeper atmospheric probes, surface rovers, and even future aerial vehicles, expanding our understanding of planetary evolution and extremophile biology. As these cities drift amidst the Venusian clouds, they stand as monuments to a singular question. In the vast, varied tapestry of the universe, what other impossible havens await human innovation, and what forgotten worlds might yet yield to persistent exploration?